and metal sputtering will be the week after that. They should both be at noon Central Time on Tuesdays. And we hope you can join us. Today, Karthick is going to explain photolithography, discuss tool capabilities and process tips, and announce some recent process developments related to using small samples at HMNTL. Karthick received his bachelor's degree in electronics and communication engineering in 2013. He started working as a process engineer at the National Nanofabrication Center, Indian Institute of Science in India. He worked on thin film and photolithography equipment, maintenance, process development and troubleshooting, and training students and users to operate equipment. In December 2019, he joined us and started working as a research engineer at Holonyak Lab, taking care of photolithography and thin film equipment. We appreciate him giving this webinar today. Go ahead, Karthick.
Thank you so much, Mark, for your introduction, and good afternoon, everyone, and thank you for joining us. So today I'm going to talk about photolithography and the recent process developments which have carried out at HMNTL. So to start with the general introduction to photolithography. So photolithography, basically we use the light energy, just passes through the patterned photomask. So whatever pattern you have it on the photomask, which will be transferred to the silicon wafer. Since silicon is not sensitive to UV light, so we use something called photoresist, so which is a temporary coating which helps us to transfer the patterns. So below I'm going to show you the animation how the general photolithography works. So we take silicon wafer or any other substrate, then we spin coat the photochemical, which is photoresist. So then we use the patterned mask and photo mask, which consists of the quartz as well as the chromium. So when when you expose to the UV, it will allow only the uncoated chromium region to pass through the UV and blocks it wherever there is a chrome present. So you have a UV source, then you have optical system. So the optical system will guide you to get your UV light exactly parallel to the mask so that you'll get the uniform exposure across the wafer. So once you expose, the exposed region will get cross-linked, so change the property of the photoresist in that region. And the next process, you do something called development. So you mass it into the chemical, so which will dissolve the photoresist from the exposed region. So at the end, you will get the exact pattern transferred to your wafer from the photomask. So photolithography involves many steps. So these are the steps which we generally use. So it will start with the wafer cleaning or a surface cleaning, and the dehydration bake and the wafer priming, spin coating of photosensitive chemical, which is photoresist, then soft or pre-bake. So then we'll expose using any of the mask calendar or a direct writing system. So then we develop it to remove the photoresist from exposed region. And the last step would be hard bake if you're going for any etching process. So what is wafer cleaning and why do we need it, right? So when you take any wafer, it will be having metallic or organic contamination or some particle or any other visible particle. So that can cause a series of problems during your subsequent process. In order to avoid that, we will be doing the wafer cleaning. So generally we do these three kind of cleaning. So start with RCA cleaning. So it's like RCA1, RCA2 to remove the metallic and organic contamination. And the second step of cleaning is something called a Furana cleaning, where you use sulfuric acid and hydrogen peroxide to clean the surface. And the third one is a solvent clean, so where we use the common solvent like acetone, IPA to clean the wafer. So the next one is called a dehydration bake. So why do we need dehydration bake, right? So at the end of any cleaning process, we clean the wafer with the DI water. So though we dry it with nitrogen, there is a chances of having the moisture on the substrate In order to remove that moisture, we do the dehydration break. So typically, it is done on the hot plate at 90 to 110 degrees Celsius. So about 5 to 10 minutes. So during this time, if there is any water residue on the surface, it will get evaporated. And the next one is called wafer priming. So this process we do in order to improve the adhesion between substrate and the photoresist. So usually we use the chemical dot HMDS to improve the adhesion. So where HMDS, there are the dedicated HMDS coating equipment at HMNTL where you place your wafer and heat it up to 110 degrees Celsius. Then you will purge the HMDS in the wafer form. Then you'll get a very thin monolayer of HMDS coated on your surface. So once you coat the HMDS, the next process would be spin coating your photoresist. So basically, photoresist is a temporary coating which will help you to transfer your pattern from the photomask to the substrate. So the photoresist broadly we can categorize into two categories, which is a positive and negative. So these are the common positive photoresists you could find on the market. So AZ1514 and S1805 and AZ1505. So whereas in negative series, it's like AZ10 2020 or 2070 and different SES series. So what is positive and negative photoresist, right? So if it is a positive photoresist, the exposed region get removed after exposure. So whereas in the negative photoresist, the unexposed region going to remove. So the next slide will go detail on how it's going to happen. So as you have your photomask, then you have UV source, when you're going to expose. So in this diagram, you can see in this region exposing the photoresist. If you are using the positive photoresist, so wherever the UV exposure happens, so that region will dissolve the photoresist during your development time, so which is positive photoresist. In case of negative photoresist, the exposed region will stay and unexposed region gonna get developed. So this is the case of negative photoresist. So based on the process, we choose either positive or negative photoresist. And the next step would be how do we apply this photoresist? So general method is the spin coating most commonly used in all the research region, right? And typically the spin coating will happen in this mechanism. So you have a chuck which have a vacuum in the middle. So we'll place the wafer on top of it, and the wafer is held by the vacuum. So then we'll dispense the photoresist on top of it. For the good practice, if you're using full wafer, we recommend you to cover only 1/3 of the wafer with photoresist, so you're not over pouring and wasting your photoresist. So typically the photoresist spin coating happen in 4 different stages. The first stage where you place your wafer and dispense the photoresist, and the second stage we slowly increase the RPM with slow acceleration. So in that a period of time, the photoresist eventually spread across the wafer slowly and uniformly. And the next step where you ramp up to the final RPM to get the desired thickness. So in that duration, it will remove excess amount of photoresist from your sample. At the end, you will get very uniform coating. So as you can see from the graph, so it's recommended to use a 3-step program to spin coat the resist so that you will get very uniform and without any artifact in your coating. So at the first step, you start from 0 to the slow spin coat. So it's slow. Generally, it will be 500 to 1000 RPM. So where in this region, your photoresist spread across the wafer very uniformly. So then you increase your final RPM, so which is the level out step. So where you will get the desired thickness of the photoresist by controlling your RPM. So typically this will happen between 3000 to 6000 RPM. At end of this step, you slowly reduce the RPM and gradually move it to 500 or 1000. Then you can go to 0. So you do not want to suddenly stop your spin speed from 6000 to 0. So that's why we introduce this slow stop step. So slowly you bring the RPM to close to 1000 or 500. So then eventually you'll reach it to 0. If you've done the very good coating without any problem, your wafer supposed to look like this without any artifacts, any defects. You'll get a uniform coating. So in case if you run into any problem, so you might find these are the common spin coating artifacts you can find. So in the first image, you can see as you dispense the photoresist onto the wafer, you make sure you do not have any air bubbles onto them. So this happened mainly because you have a faulty pipette or a dispenser, or you did not close your photoresist bottle properly, which can accumulate the nitrogen air bubbles over a long period of time. So when you dispense the photoresist, you make sure you do not have any air bubbles on them. And the second one is streaks. In case if you have any problem with your cleaning, where you did not clean it properly, it leaves some of the particles on the wafer, or the particles can be transferred from your photoresist also. So during spin coating, all these particles obstruct the photoresist and it will leave you streaks and ununiform coating, which will eventually affect your features during the development. So in order to avoid it, you make sure you do the very proper cleaning of the wafer and it should not have any particle. All right. And the second major thing it happened from your photoresist also, which is when you do not use the photoresist for a longer period of time, at the nozzle, it can get dried off. Then you open the bottle, so all these dried particles can fall into your photoresist and make this particle. So make sure you properly clean your photoresist bottles often. It's free of particles. And the third one is if you have a very high exhaust and very high RPM or acceleration at the first step, you will get this kind of swirl pattern. So what will happen is when due to the sudden change in momentum, so whatever photoresist you poured in the middle, it will flash across the wafer, which will make this pattern. So due to this high acceleration and the speed, it will leave some uncoated region, and you might get the center circle. This is basically due to your vacuum suction. So your vacuum suction is too high, may make a small bow at the exactly center of the wafer, so that you might get slightly change in your photoresist thickness. And the fourth one is something called restoration. So this is due to very high solvent evaporation during your spin coating. In case of your spin coating has a very high rate exhaust, so which will during your spin coating, it will ununiformly evaporate the solvent from this region, so it can leave this kind of striation mark. And the last one is edge beads. So when you use any substrate other than the square, other than circle, if you're using square pieces, only you would get uniform coating at the center, and it will leave this ununiform coating plus edge bead on the edges. So during spin coating, it works in the basic principle of a centrifugal force, where you use a circular wafer, the force will be equal from the center to edge, but whereas in square pieces, it's not the same. So at the edges, always you'll find a little bit of thickness variation. So if you're planning to use any smaller substrate, always concentrate your pattern on the middle, this uniform region. You do not want your pattern to be on here. So in case if any of your pattern fall on this region, you'll end up getting ununiform development rate due to the photoresist thickness variation. So once you do the photoresist spin coating, so next step called soft bake. So in this step, basically we will be removing excess amount of solvent from your photoresist. So all these photoresists have some amount of solvent to make them in the liquid form. So once you're done with your spin coating, you do not want that solvent anymore to be on your wafer. So in order to remove the solvent, we usually do the soft bake. So typically this will happen between 90 to 110 degrees Celsius, about 1 or 2 minutes. In case of if you're using conventional oven, you'll be doing in 10 to 20 minutes based on the thickness. So the pre-bake is very important. If you do the lesser pre-bake, you'll be leaving more solvent in your photoresist, so which will dilute your developer during your development stage. So basically you'll end up getting very high development rate. So in order to have a controlled development, so necessary and appropriate soft bake is needed. And in case if you're using hot plate, you make sure you have a very smooth bottom surface so that we'll get very good thermal conductivity and uniform baking across the surface. So once you're done with your soft bakes, the next step you'll be doing the exposure. So at HMNTL we have a different equipment to do the exposure. So we have a Heidelberg, which is direct wetting system. Then we have MJB3 and EVG620. So each of these equipment have its own wavelength. So if we talk about wavelength, Heidelberg have 375 nanometer laser, and MJB3 has 365 and 320 nanometer UV source, and EVG620 has again 365 nanometer UV source. So in terms of exposure method, Heidelberg is a direct wetting system, so it will expose point by point based on your design. And MJB3 is a parallel exposure, so it will expose the entire field at once. And EVG also it's parallel exposure. And the exposure modes, Heidelberg it does the direct wetting. It's driven. I mean, you just feed your design into the system. So based on your system, it will control the laser and does the writing. And MJB3 we have 3 different contact modes: soft, hard, and vacuum. And EVG620 it has 5 different contact modes like soft, hard, vacuum, vacuum plus hard, and the proximity. So in the next couple of slides we'll discuss briefly about this contact mode. And the maximum exposable area in terms of Heidelberg it's 5-inch and MJB3 3-inch. EVG620 we can expose up to 6-inch wafer area. And substrate size in Heidelberg you can use even 5 mm samples to 6-inch sample, and MJB3 you can use it from 5 mm to 3-inch wafer. EVG620 you can use again from 5 mm to 6-inch. So when you load your mask and the wafer into any mask aligner system, it some of the tools it automatically does something called wedge error compensation. So in this step, it will make your photo mask and the substrate exactly parallel to each other to get uniform exposure, across the area. So you do not want any proximity effect or a gap between your substrate and the mask during your exposure. So whereas in MJB3, you will be doing manual WC, you load your wafer and substrate, and you'll be slowly increasing your Z height. And once the wafer and the mask make contact, then you'll stop it. But whereas in EVG, the WC mechanism works automatically by itself. So this is a cross-sectional view of cross-sectional image of EVG620 WC mechanism. So where you'll be loading your mask the top with mask holder, and your wafer will be loaded here. So once you load your mask and substrate, the system automatically perform wedge error compensation. So where you can control your WC pressure. Basically, you can give how much pressure you want between your wafer and the substrate during this process. So EVG is 500 millibar in generally we use. So the system automatically apply 500 millibar pressure, and it will release the stage. So the stage will have a spring action at the bottom, so it can move in any direction. So when it moves close to the wave, your mask and the wafer, it will adjust the wafer according to the mask plane. So it will make your mask as well as the wafer exactly parallel to each other. So during this stage, the wafer and the mask both held by vacuum, so you do not have any movement in your mask or a wafer during this WC process. So the next stage, in terms of if you're using any of the mask aligner, either EVG or MJB3, you'll be having a different contact mode. So you can choose any of this contact mode based on your critical dimension and the application. So here I'll explain about the different contact mode. So let's start with soft contact. So you have a chuck and you have a mask holder, your mask photo mask and substrate both are loaded and they're both held by vacuum. During exposure, if you choose to use soft contact, it will activate the vacuum through your chuck. So your wafer is held by vacuum and it just firmly touching your mask. So there is no pressure between your mask and substrate. So your mask is just firmly sitting on top of the wafer. So this is called soft contact. So if you have any features close to 10 micron or more than 10, so you can easily get those features by using this contact mode. So whereas in the next one is called hard contact. So hard contact mode, instead of the vacuum, the system activates the nitrogen purge. The system activates the nitrogen purge, so it will push the wafer against the photomask. So which means it's hardly pushing the wafer very hard against the mask, which will not have any gap or any proximity between your substrate and mask. So in this contact mode, you will get very good features compared to soft contact. So whereas in the next one is called vacuum contact. So this, if you are going to use vacuum contact, you make sure you use O-ring on the wafer chuck. So what will happen is the chuck will have two different vacuum lines. So one is at the boundary, one is in the center. So this one is used to, hold your wafer during the process, and this one will create a vacuum between the mask and substrate during the exposure. So once you load wafer and mask, you perform Wedge compensation. So when you move to the exposure, system will automatically activate the vacuum at the center, which will be holding your wafer. And the next step will activate this vacuum. So it will evacuate whatever air between your substrate and the mask. So then it will allow the exposure. So which means you'll get very good printing compared to hard contact, because you don't have any gap, as well as the whatever air atmospheric gas between your substrate mask, you remove it. So you'll be avoiding all the diffraction effects. So you'll get very good print using vacuum contact. And the next one is called vacuum and hard contact. This contact mode is basically the combination of vacuum contact as well as hard contact. So what will happen is initially the system will activate the vacuum here. So it will remove whatever atmospheric gas between your substrate mask. So, and then the system will activate the nitrogen purge. It'll, once you remove the air between your substrate and mask, then it will push the wafer against your photomask. So in this contact mode, you'll get very good printing. But the problem here is, since you're applying too much pressure on your wafer, at the long run you may end up damaging your photomask due to this high contact force between your mask and the wafer. The last one is called the proximity contact mode. So whereas in proximity, your substrate and the photomask will never make contact. So always between your substrate and the mask, there will be a gap. So in EVG, you can control the gap between 1 micron to 200 micron, so where you will never make contact between your substrate and mask. But since you have a gap between them, you cannot get any fine features like less than 5 micron features. So if you have a feature that's more than 10 micron, you'll get very good prints. But if you're using proximity contact, you'll get very good photomask, durability and lifetime, because it will never make contact with your substrate. So this is the pros and cons of the different contact mode. So listed from proximity to vacuum plus hard. So for better resolution, you need to use vacuum plus hard contact. And since you have a very high contact force between your substrate and mask, you have a very less mask durability in this contact mode. So every time when you make contact between your substrate and mask, some amount of photoresist can be stick to your photomask. At the long run, you will be damaging your fine features on your photomask. In other cases, in case if you have any particle during your spin coating, during this contact mode can be crushed between your substrate and mask, that can again damage your photomask and the chrome. So based on your process, you can choose any of this contact mode and use it. The next step, if you're using any of the contact modes, probably you'll end up getting some contamination or a photoresist residue on your photo mask. So these are the three common methods to clean the photo mask. The first one is called soap water clean, where you put your mask into the soap water and take some very fine foam and slowly you can rub it and clean the residue. And the second one is called solvent clean, where you use acetone, IPA to clean your residue from the wafer. So if these two clean doesn't work, then the last one is piranha cleaning. So in this case, you should be very careful because the piranha, if you're doing it for a longer duration, it might end up etching your chromium on the mask. That's why you have to do it in very diluted piranha chemical, and the duration will be 5 to 10 seconds. So this is the last and the least recommended step for any mask cleaning, because if you're not careful and doing it for longer duration, can really affect your photo mask. Which below is a picture of your photo mask features before and after cleaning. So as you can see, we are using the photo mask for a long duration. So if you have any lines or any square structure at the boundary, you will get the photoresist residue which will come from your wafer. So without cleaning, if you're using it further, you may end up getting very rough surfaces, very rough lines on your wafer. So in order to avoid that, at least you can, before every process, we recommend you to do the solvent clean to make sure you get very good print. So once you're done with the exposure, so the next step probably you'll be going for either lift off or etching process. So for lift off, you do not want to do any hard bake because you'll be removing your photoresist in the lift off process. But whereas in etching, you'll be introducing this photoresist into chemicals or a plasma environment. So your photoresist should withstand that process. So in order to increase your selectivity, we recommend you to do the hard bake. So during this hard bake process, it will remove any excess amount of solvent from your photoresist and make them harder and sustain in the etching environment. And based on the temperature and the duration, it can affect or you can control the your photoresist profile. So ideally, the hard bake happen between 90 to 110 degrees Celsius. If you're doing it close to 100 and 110 for a minute or a 2 minute, you will be getting very good profile. But in case if you increase your temperature or increase the duration, so due to the temperature effect, your photoresist will start reflowing, so that can affect your profile. But some of the process people intentionally do the reflow to get 3D structures. For example, if you have a circle, if we do the first, you can do the controlled reflow, you'll end up getting semi-sphere. So some of the 3D applications, you can really use this hard bake to control your features. And this is end of a photolithography process. And the next few slides, I'm going to explain about the few process development we have done at HMNTL. The first one, this is done it on Heidelberg direct wetting system. So one of the students want to use the substrate 5 mm cross 5 mm on the system. So we have done the optimization run on Heidelberg using 5 mm cross 5 mm structure. As you can see on your right side is a 5 mm cross 5 mm silicon wafer. It's patterned 3 mm cross 3 mm substrate. And these are the process parameters we used to achieve this process. So the main important thing in this process, we used the manual focusing in Heidelberg option. So the problem of using smaller substrate in the Heidelberg, the system has something called automatic focusing. So the moment you load your wafer, it automatically focuses the surface and does the writing. But if your sample is less than 10 mm area, the system cannot detect your sample automatically. So in that case, we need to use something called a manual focusing. So in this process is achieved by using manual focusing method. And these are the other exposure and development parameters. So for this experiment, we used 4 micron pitch grating. So as you can see the cross-sectional SEM image. It's 2.25 micron line opening with 1.5 micron spacing. And the next one is using the smaller substrate on EVG 620. So here we used the 3-inch and 2-inch chuck to get this process completed. So as you can see the image, it has a different level of, it has a different vacuum lines. So you can see the outer one, so that is meant for a 3-inch wafer, and we have one more inner circle, so which is for using a 2-inch wafer. And the middle you have vacuum line to hold anything which is less than 2-inch. So in this process, we use roughly 10 mm cross 10 mm wafer, spin coated, and we follow this particular Photoresist S1805, and we soft bake for 1 minute, 110 degrees Celsius. Exposed using vacuum plus hard contact mode, and developed using MIF developer. So by using this process, we achieved submicron features, which is close to 900 nanometer, and 1 micron features. As you can see the cross-sectional image. So to getting anything less than 1 micron, that's your photoresist thickness and the contact mode and uniform photoresist spin coating is very important, because these are the one will define your critical dimension. So if you want anything less than 1 micron, you make sure you have a photoresist close to 500 to 900 nanometer range. So at the summary, in EVG and Heidelberg, you can achieve sub-micron features if you can uh, have a very good uniform coating of photoresist and controlled exposure. And also we have extended our capabilities on EVG and Heidelberg system by using smaller substrate. So if any of you guys interested in getting smaller substrate exposure done on any of the systems, so you can contact me, you can write me email, you can fix an appointment, so we can discuss more on that. So this I'm head of my topic. So if anybody have any questions or doubts, you're welcome. Thank you everyone for listening.
Thank you, Karthik. If anybody has any questions, you can use the chat feature and type them in there. Karthik, the different modes of contact, proximity and contact and hard contact, I can understand. Can you help us understand how very different or not very different the various hard contacts are of hard contact, vacuum, and using both? And if that is very much help when I'm pushing to below a micron of printing with these types of photolithography techniques.
Yeah, sure, Pan. So yeah, where when you use a different contact mode, it has its own advantage as well as the disadvantages. As you said, if you want to get anything less than a micron or close to micron, you can use either vacuum contact or vacuum plus hard contact to achieve it. But as you said, when you doing it for a long period of time, you may end up damaging your photomask. So if you're very worried about it, about your photomask damaged, you can go ahead and using the vacuum contact. In this vacuum contact, you'll get very good print, but except you don't apply much force between your photo mask and the wafer. And but vacuum plus hard contact really affect your photo mask only at certain conditions. So where you have any particle left on your sample during spin coating, that particle get crushed between the substrate and the wafer, it can seriously damage. But if your coating is very uniform, you do not have any particles. So if you are doing it in a controlled way, it doesn't affect that much.
Thank you. So is vacuum is less damaging than hard contact?
Yes.
Very good. Thank you. What happens if I avoid using HMDS?
Okay. So HMDS is generally used to improve the adhesion between the photoresist and the substrate. So what will happen is if you have any trouble in your cleaning or you're leaving any contamination or the substrate is too much hydrophilic. So basically the substrate hydrophilic in the sense you have some water vapors sitting on your wafer surface, right? So which can seriously affect during your spin coating. So the HMDS, what it does is when you coat thin layer of HMDS on top of your wafer, it will form a wedge group on the wafer surface. So it will chemically modify your wafer substrate. So that's the one improving the adhesion between the photoresist and the wafer. If you don't use it, it doesn't hurt much. If you have a feature size like more than 10 micron or so, it doesn't hurt much. But if you wanted to have more control on your development, so it advised to use HMD. Since you have a very good adhesion between your substrate and the photoresist, during development you'll get very controlled development. You can have a control over your overdevelopment rate compared to without using HMD. So that's the difference. So it's not, even you can get a features without HMDS, but you may have very less control over your development rate.
Can too much pre-bake time negatively impact development time? Can you talk about the trade-off between your soft bake and your hard bake?
Yeah, sure. So yes, the too much of pre-bake have a negative impact on the development. So what will happen is when you bake it for too long or a higher temperature, your photoresist will be completely dried off with a solvent. So which will make the photoresist very hard to dissolve in your developers. So that's the reason you have to make a sufficient soft bake, not too low or not too high. So when you bake it very less, you'll be leaving too much amount of solvent, which can increase your development rate. But if you bake it for too long, your photos will be really dried out and it will increase your development rate very much higher. So it's a trade-off how much you do it. So that's why always, it's recommended to do the hard bake between 90 to 110 degrees Celsius, and the time should be 60 seconds to maximum 90 seconds if you're using any photoresist, between 1 to 2 micron. But if you're using any photoresist, it's more than 2 micron. For example, if you're using anything called AZ 4562 or 9000 series, where your thickness will be more than like 3 to 4 micron. So in that case, probably you can increase it like 2 or 3 minutes. But it's always a trade-off between your soft bake and the development. So either you increase or decrease your development time, which will have an impact in your, sorry, if you increase or decrease your baking duration, it will have a direct impact on your development rate as well. So that's the reason we always fix the timing between these windows. You don't increase or reduce it too much.
Is there a way to remove edge beads to get better contact between your mask on small chips? Can you comment on managing edge beads on odd shapes and making good prints?
Okay. So for a smaller substrate, you'll anyways get edge beads. So in order to remove it, you can use the solvents and the Q-tips. You can slowly, wipe the edges to remove them. So that's a one way. And second way, if we can afford more samples, so instead of spin coating exact sample, you can increase your sample size. For example, for your process, if you need 10 mm cross 10 mm sample, you can spin coat something like 15 mm cross 15 mm. So after your spin coating and baking, you can just scribe those outside region so that you will get only the uniform spin coat region at the middle. That's one. These are the two options you have. Because in spin coating, you cannot avoid edge beads on the smallest sample. So that is impossible. The only way is after spin coating, either you remove them with solvent or you can scrape some of the wafers out to get uniform coat.
What are you using for Piranha etch? Where do you get it from? Do you mix it yourself?
Yeah, basically you can do it 1:6 or 1:10 ratio. So we can mix it at our lab, H2SO4 and hydrogen peroxide at 1:6. We'll use it. Plus, you don't get Piranha ready-madely available, but there are some companies uh, providing ready-made mask cleaning chemicals. So if you do not want to use Piranha, probably you can purchase it from them.
But you mix yours yourself?
Yes, yes, I'll mix myself at HMNTL.
Can you comment on the effect of transparency of substrates? For example, gallium nitride or silicon or glass or sapphire. How does that affect dosage, resolution, profile, and outcome of an image?
Okay. So yeah, so difference between using a transparent substrate and the silicon. So silicon, when you expose it, it kind of absorb your UV. You do not have, there is something called the backside reflection. So you won't get any backside reflection in silicon. But whereas when you use the transparent substrate, you will get something called backside reflection since your both surfaces are smooth, so which can unintentionally expose the whole wafer. So that's why you always find the variation between, I mean, those variation between your substrate, silicon substrate versus transparent substrate. So in order to use any transparent substrate, usually you can control it along with your baking and the exposure. So you can have a little bit extra soft bake and you can reduce a little bit of your exposure duration. So by varying your soft bake and the exposure, you can get better features in the transparent substrate. So in other cases, instead of directly loading your transparent substrate on the chuck, you can use some silicon wafer as your backside absorbing substrate. So then you can put your top on top of it. You can use the transparent substrate instead of directly using it on the chuck. So these are the ways you can improve your process on the transparent substrate.
A hard bake question. Will post baking at 140 C affect the photoresist removal after the process?
Yes, it can affect because most of the photoresists at max, nobody uses anything more than 110 degrees Celsius. But at 140, if you're taking it for more than like 2-3 minutes, it should not be a problem. But more than that, you might have trouble removing in the salt. Probably you cannot remove it in solvent. You may need piranha or some strong strippers to remove the PR if you hard bake at very high temperatures.
Let's return to Piranha.
Okay.
If you use Piranha to clean a chrome mask, how do you manage its aggression on removing the chrome?
Okay. So main reason, piranha, your chrome can be dissolved in piranha solution. So that is the reason we are diluting the chemical. Instead of using it high concentration, we use very, very low concentration. And again, we do not use it more than 10 to 15 seconds. So as you keep it for a minute or so, what will happen is it will start affecting your line edges. So instead of having smooth line edge, you'll end up getting very rough surface. Either, I mean, if you don't control your time on the concentration of the solution, in case if you have any fine features close to less than 5 micron, I don't recommend you to put it in more than 10 seconds. So it's like a quick dip and you take it out. You do not soak it for a long duration, so which can really affect your pattern. Yes.
can you use RCA1 to clean masks or some other organic, gentler cleaner on a mask than Piranha? Are there other common cleanings that you're familiar with than the 3 that you mentioned in your talk?
Yeah, sure. But whatever I mentioned, like either solvent or soap water or piranha cleaning is the mostly used one. But RCA1 nobody prefers because RCA1 you'll be using very strong chemicals, so which can have some effect on the glass as well as the chrome. So that I wouldn't recommend using RCA1. So the best option is either you can go for soap water clean or a solvent. So if that doesn't work, then you can go for a very diluted and quick piranha clean rather than using RCA1.
Thank you, everyone, for attending. If you have additional questions, curiosities, or any kind of struggles with photolithography, Karthick is happy to help. And during these times of very lightweight laboratory use, feel free to use that time to contact him or any of the engineers at Holonyak Lab. We're happy to help or have discussions about your process issues. Next week's seminar will be on metals evaporation, and we hope you can join us then.